Okay, so yeah, so I would prefer to use the alternative title of In Defense of Bucketing, given that this is a very hot topic. So this is a talk in honor of Dana, continuing the program from yesterday. And it's on a problem where bucketing is in some sense provably needed and important. Okay, so let me start with a simple bounded query setting. So we're given query access to a function, f from some domain size n to itself. And let's say that we want to find a collision in this function. So we want to find 2 points, x and y, so that f of x is equal to f of y. This is a collision. It's a very simple but important object. For example, in cryptography, we want functions that are collision resistant, hash functions. And basically the meta question that I want to ask is the following. So does knowing the structure of the input help us solve the given computational problem, for example, collision detection? And I would use a notion of instance optimality, specifically unlabeled instance optimality. So let me define to you what I mean by instance optimality here. So this definition, so there are various notions of instance optimality for different problems. It typically depends on the structure of the problem that we want to solve. We will use, as I mentioned, the notion of unlabeled instance optimality. Oh, I mentioned the alternative title, but I didn't mention the co-author. So this is joint work with Tomer Grossman. And Monino. Weizmann Institute. Okay, so definition of unlabeled instance optimality, and this is from an earlier paper by Tomer, Ilan Komorgodsky, and Moni, is the following. So let's say that, so we have 2 types of algorithms. One is the algorithm that is only given. So again, we have a function from some domain to itself. And on one hand, we have an algorithm that doesn't know anything about the input. It knows n, but it doesn't know anything else about the input. And it tries to find, for example, a collision just given queries to the input. On the other side, so this is just a standard algorithm. We don't know how to call it. On the other side, we have an algorithm with a certificate. This algorithm knows exactly what is the structure of the function. So let's say that the structure looks like this. We have this. This, for example, is a collision. And it has say this, it knows exactly what is the structure of the input. I said unlabeled to certificate, and by this I mean that it knows exactly. So if we kind of remove the labels, remove the names of all of the elements, so this is a structure that the algorithm is given, and on top of that it is given the same query access the original algorithm is given. So here we only have query access. To F, and here we have this certificate plus query access. All right. Any questions about this type of algorithms? Okay. So I wanted to ask for your opinion. Okay, so there's a spoiler in the abstract of this talk, so maybe some people already have some opinion because they read it, but if you haven't read it, I wanted to ask for your opinion. By what amount do you think that an algorithm with an unlabeled certificate, that algorithm that knows the structure of the input, by what amount do you think it can accelerate the algorithm? So what is the largest gap that you think there is between the query complexity of finding collision detection, of finding collisions between an algorithm that knows the certificate and an algorithm that doesn't know the certificate? Okay, square 10. So yeah, who thinks it's polynomial? Or logarithmic? Constant? Okay. The answer is we don't know for sure. It's not a constant. Conjecture it's logarithmic, but we'll see what we know. Anyway, so by unlabeled instance optimality, I mean that so an algorithm A is unlabeled is alpha. Well, alpha can depend on n if it's a class of problems that of different sizes. So it's alpha unlabeled. So it's optimal if the expected number of queries for finding a collision in F for this algorithm A is at most alpha times minimum over all possible algorithms A prime of the same expectation of A prime on F given a certificate. Okay, let me try to convince you it's maybe that it's not a constant.
For all F before.
Yeah, so it's a minimum. It's for all over all algorithms A prime.
This holds for all F. For all.
Yes, right. Okay, so let me try to convince you why it's not a constant, maybe. So if, for example, we knew, okay, so I guess the first kind of, so let's say that you know nothing about the structure of the input. You're only given query access to it. So maybe one way one thing we could do is to just start from some random point and maybe start walking until we hopefully find a collision. This could be maybe, I don't know, useful for certain inputs, but if the input, but if, for example, the structure of the function is such that all of the collisions happen very fast, for example, like something like that. So let's say that the input it contains a union of structures like this and maybe long cycles or something like that. So it is more beneficial to try walks that are relatively short and not spend a long time working on cycles that may be long. So sometimes the strategy of walking for long is not beneficial, but in other cases, it is beneficial to walk for long. So for example, if collisions happen after a long time, so I can show you some numbers, but there are instances for which you definitely want to try to like hit this part of the walk and which like collides into itself. So the main result that I would like to present is a characterization of instance optimality for problems like this. It's not complete yet, but it's almost complete. So let me tell you what we know. So the main result is a characterization of instance optimality for the problem of detecting some subgraph or some substructure. And I can also present you the model for graphs. Or substructures in a function or subgraph in a graph. So the equivalent model for graphs is instead of getting query access to the function, we have just the usual query access to graphs. So we are able to access any vertex that we haven't visited so far, so like a random vertex, or we can get the degree of a vertex or the list of neighbors. So the analogous model for graphs is just the adjacency list model, although it doesn't really matter. The result will be more or less the same for the adjacency metrics model, which is like what is called the dense graph model. So the main result is a characterization of instance optimality for detecting substructures or subgraphs. And there seems to be a trichotomy. We are not able to fully characterize it, but it seems like it should be a trichotomy. So for very simple problems, let's call the substructure or subgraph, let's call it H. So this will be for functions. This will be for graphs. So when the substructure is very simple, so for example, in functions, the substructure is just a simple pass. So there's not much you can do if you want to detect a pass in a function. Just try to walk for a certain amount of steps, and if you manage to do that, then you succeeded, and if not, you can try again. So there's not much you can do. For this, this type of problems is O of 1 unlabeled instance optimal. So there exists an algorithm that is O of 1 unlabeled instance optimal for this problem. And similarly, there are also problems in graphs that look like that, and they are very, very simple objects. So if you want to detect a single edge or a wedge, so two edges, this is also O of 1 instance optimal. The second type of objects are ones that are far from instance optimality. And for those objects, I would say, in some sense, maybe we need to look for a different model of instance optimality to maybe perhaps capture what is interesting. So for any h that is not a path, okay, so maybe there's the most concise representation is h that contains at least two collisions or a fixed point. So this is an example of such h that contains two collisions. So the type of structure that contains two collisions, or a fixed point, which is a structure that looks like this, like a function that an element that is pointing to itself. So for this, we have a big separation. So we have a polynomial separation. And analogously, in graphs, any h that is not these two graphs, so a single edge, wedge, or so this is a star. If you think of it as like a star is a graph that has like a central vertex and legs that go from this central vertex. So this is a star with one leg. This is a star with two legs, and a claw, which is a star with three legs. So any fixed graph that doesn't look like one of these three and that is not empty. Also, we have so all of these problems are n to the omega of 1 far from instance optimality. So any algorithm for these problems is not n to the little o of 1 instance optimal. And what's most interesting is that there seems to be a middle regime. There seems to be an intermediate regime between the two. So for detecting collision, the functions, or for detecting a claw in graphs, let's start with three legs. So we know a logarithmic separation. And for claws specifically, we have some indications that it might be tight. So for claws, in some special cases of instances, or instances where the complexity of finding a claw with the certificate is relatively low, we also know that it is tight. And also the lower bound applies in this case. So we know that it is theta of log n in some cases. Any questions about it? Yeah.
Just to understand better. So when you say overlapping, you mean you design some instance optimal algorithm that finds claws that.
Yes, and and more or less the same kind of algorithm should also work for collisions, but we don't know how to prove it yet. We're pretty sure about it.
Log n times optimal for all.
Yes, and it is an algorithm that does bucketing. So, or an analysis that does bucketing. The lower bound is very bucketing heavy in some sense. This is the proof of the lower bound here. Any other questions? I don't have a lot of time for to go into a lot of details. So if you have questions about the model, I'd be happy to take that. Sure. But I want to point out that, I mean, this is just one model of instance optimality, and when you try to analyze your favorite problem, in this case, favorite graph, or like combinatorial structure detection problem, it's very useful and very interesting to analyze these kind of problems also in the instance optimal setting. So even if the worst case complexity of your favorite problem is already resolved, most likely that the instance optimal understanding of the problem is still not there. So it's relatively not a well-developed area, at least in the combinatorial setting. There are some works in, for example, in distribution testing. It's more well understood, and there are some sporadic problems. So, for example, in geometric problems in low dimension, where there are results about instance optimal algorithms, but results about detecting or counting or approximate counting structures don't seem to exist yet. So, so before I go into technical details, I want to point it out that it's relatively wide area to explore. All right, so yeah, I can tell you a little bit. I can tell you about the candidate algorithm for optimality. So we've seen here that. So I told you in. Wait, not sure. So I told you that in some cases it may be better to walk for short distances because there are many collisions that can be found after just a few steps. And there are many instances, and there are other instances where it's better to work for long. So this is the candidate algorithm that we know that it is O(log n) optimal in some cases. And we conjecture it's always O(log n) optimal. So the algorithm is pretty simple. So you start, so you run basically log n walks in parallel. So this is how the first log n steps look like. And then, so this walk will try to conclude after the ith walk here will try to conclude after 2 to the I steps, and we run them in parallel. So this walk is going to be of length up to 1, and this walk is going to be of length up to 2, and so on. They might terminate early because they, for example, close the cycle or something like that, so they cannot continue anymore. So this walk is going to be of length 2 to the I. And it turns out that so this algorithm doesn't need a certificate. It doesn't need to know anything about the input, and it seems that so at least in some cases we know that this algorithm is log n optimal for finding collisions, and also for finding close. So maybe for in the graph setting you might want to walk not just forward but also backward in both directions, but it more or less looks the same. Yeah, so this is the algorithm that we conjecture is optimal, and I don't think I have time to go to tell anything meaningful about the analysis. So let me maybe stop here.
Thanks. Is there any question for Omri? I have actually one question, which is, so this is, I guess, one way to define instance optimality. Can you comment on like what would be other ways to define it and why this one might be better? Like, how did you converge to this particular option?
They don't dominate each other. I mean, so certain models are relevant. I mean, it's very problem specific. I think, I mean, this kind of model, for instance, optimality in our case is very strong, right? So, I mean, you assume that so I know if I'm running some algorithm on a graph where I have some guesses about what its structure will be like. So the question is like, to what extent like this knowledge about the graph will accelerate my algorithm? And this is a very strong form of knowledge. It tells us that we know exactly the structure of the graph. And even with this very strong form of knowledge, it seems that there are non-trivial, almost instance optimal algorithms. So for the problems of finding a collision in a function or a claw in a graph, the distance from instance optimality is only log n.
So Yes. It's third speaker. Yeah. Third behind the color.
Thank you. Thank you.